Okay, in this presentation we are going to look at probability distributions and random number generation. So there's quite a lot here, so we'll get stuck into it. Let n be an integer, and suppose that x1, x2, x3 all the way up to xn are independent random variables, each having an exponential distribution with a rate parameter lambda. Okay, so essentially that's the first piece of information. Now, show that z, or z, is equal to x1 plus x2 all the way up to xn. So it's the summation of all of these exponential random variables. Show that that has a gamma distribution with the parameters n and alpha. Okay. Now, so that's the first part, and then by using this result, generate a random sample from a gamma distribution with mean 30 and variance 300 using the following 5-digit pseudo-random numbers. So here we have three pseudo-random numbers: 63,293, 43,937 and 08513, 8,513 with that 0 there. Okay, so we have those three 5-digit random numbers. Now, so essentially the first part is that we're going to rely on the moment generating function. So let x be a random variable, okay, and the moment generating function mgf of x is denoted as follows, or it's defined as follows. So we denote it as m of x, mx of t, and that is the expected value of e to the power of t times x. Okay, x is the random variable. Okay, so that's straightforward enough. Now, the important thing here is we're dealing with the powers of exponentials. So just recall that the exponential of a plus b, or e to the power of a plus b, that is e to the power of a times e to the power of b. Okay, those rules are very important. Now, so if y is another random variable and z is the sum of x and y with z equal to x plus y, this is how we would define the moment generating function of z, which is the expected value of the exponential of t times x plus y, and that is equal to the expected value of e to the tx times e to the ty. So that's important to remember that stuff there, because we're going to use that in our calculations here shortly. Okay, so this stuff is very important. So let's move on. So this is an important definition here. Now, this is something you'll probably be given in the back of your exam paper. Each exponential random variable xi has the moment generating function as follows. Okay, so it's lambda divided by lambda minus t for t less than lambda. Okay, so that's the first important part. Now, this is consistent for all of the n exponential random variables. Okay, now, so the moment generating function of z, which is the summation of those, is as I said, the summation of those individual x random variables, which are exponentials. And sort of following from the definition, or that I've just used there, the identity or the approach that I've sort of outlined here, that's essentially the product of them all. Okay, and because they're pretty much the same the whole way through, lambda divided by lambda minus t, essentially what we have here is we can just put them to the power of n. Okay, so there's n x variables, n exponential random variables. So when the moment generating function of that is the moment generating function of each individual variable times the next one, so on, and we end up with lambda divided by lambda minus t to the power of n. Okay, now this is the moment generating function of the gamma distribution with the parameters shape parameter n, which is also denoted alpha, and rate parameter lambda, which is also denoted beta in other cases, and hence the z random variable has this distribution. Okay, so just a couple of points there. This is how we would define it, as a summation of exponential random variables with shape parameter n and rate parameter lambda, but in the generic notation would use alpha and beta. Just the sort of one explanation that would sort of be the difference of the two is that in this context n is specifically an integer, whereas for the gamma distribution it does allow a shape parameter that could be a real number, a fractional number. So that's why you make that distinction there, n and lambda, just to sort of highlight that n is an integer and it sort of has an application that ties in with the exponential distribution, but the gamma distribution has other applications beyond that. So the generic one will be alpha and beta. That's really it. Now, how would you know that that was the gamma distribution? Essentially, you just check the back of your exam paper and just sort of see, does that fit? Now, just as a quick remark, you could get something like this in the back of your exam paper: lambda minus t to the power of, or divided by lambda to the power of n minus n. Okay, and that could be equal to 1 minus t divided by lambda to the power of minus n, okay, or minus n, and that would be a form that is consistent with what you might read in textbooks, that form there, but it actually is numerically the same. It's just arranged differently. Just watch out for that. So the second part is we're going to do a quick random number generation, okay, a simulation. Okay, so let's just read the question again. By using this result, generate a random sample from a gamma distribution with mean 30 and variance 300 using the 5-digit numbers given below. So the first thing we have to do is actually figure out what the specifications are. The parameters are for the gamma distribution. Now we're told the mean and the variance, so that means we can figure out what alpha and beta are, which is also n and lambda. Okay, so that's what we're going to do here. The mean is 30, so alpha is the mean squared divided by the variance, which is 30 squared divided by 300, which is 900 divided by 30, which is 3. So the shape parameter alpha is 3, and that's also n. Okay, so n is 3. Okay, that we're going to use that in our approach. Beta is the expected value divided by the variance. That is 300 divided by 30. That is 0.10. That's a mistake there. 0.10. So that's beta, which is the rate parameter, which we're also using the notation as lambda. Okay, so the random number can be generated by producing n equals 3 independent samples from an exponential distribution with rate parameter lambda equals 0.1 and adding them together. Now this should be straightforward enough stuff. This is the most straightforward fundamental example that will be given to you when you're starting to do random number generation and Monte Carlo process and so on, how to randomly generate an exponential random variable. Okay, so to do this, what we do is we solve f of x, okay, that's the cumulative distribution function of x, and that is 1 minus the exponential of minus 0.1 times x, and let that equal to u, where u is a pseudo-random number generated from a uniform distribution on the interval 0 to 1. Now, I'm rushing through this. If you're not familiar with this and where this is coming from, you probably just sort of skipped a step and need to go back and look at this, because this is sort of the first thing you'd sort of come across in random number generation. And if you're not familiar with it, you're probably going a little bit too far here, that you really want to be sort of clear about what's going on here. This should be very straightforward. And if not, just stop a second and go back and look up this stuff. Okay, so essentially what we do anyway is we arrange this expression here, so we have it in terms of u, and that's what we get. X equals minus the log of 1 minus u divided by 0.1. Now, just as a sort of quick remark, that something that's also perfectly valid is log of u divided by 0.1. I'll do it this way for this particular video, but this actually is also a valid approach because 1 minus u and u have the same distribution. Okay, so using our pseudo-random numbers to give from the exponential samples, we have the following. So essentially turn this into our 5-digit numbers into an observation or vary it from the uniform distribution. So essentially just put a decimal place in front of it. U equals 0.63292. That will give us a value of x equals 10.022 using this formula here. Okay, When u is equal to 0.43937, that will give us 5 equals x equal 5.787. And when u is equal to 0.08513, that means x is equal to 0.890. Okay, and therefore the sample from the gamma distribution is the summation of these three numbers, which is 16.699. And that is the answer there. Now, just actually as a quick remark, if you take a different approach using this, you will get a different number, but it's equally valid. Okay, but just sort of explain what you're doing. Okay, a sensible examiner would look out for this as an equally valid approach, and if not, call them up on it. Okay, we'll leave it there.